We also have Boolean theorems of several variables. So some of them are similar to or exactly the same as regular algebra. So for example, we have commutativity, where across an and relationship, the terms can commute or move. B and C is the same as C and B. Or the dual form, where we replace the and with or. These terms can also commute across an or relationship. Associativity, right? If we have more than two terms anded together, we can perform B and C and then and the result with D as a second step, or perform C and D and and the result with B as a second step. So across an and relationship, associativity holds, and same thing as across an or relationship, associativity holds. Distributivity, B and C or D. B is equal to B and C or B and D, similar to what you've seen in algebra, right? B and C or B and D. This dual form is different, right? In regular algebra, we do not have this dual form. So B or C and D, this or can also distribute across this and. So we get B or C and quantity and, here's our and here, B or D. So this form of distributivity, this dual form, is different from algebra. We cannot do that in regular algebra. Covering, B and B or C equals B. So B or B and C equals B. They're both forms, the theorem and the dual form of covering. And combining, B and C or B and C bar equals B, and then the dual form of that. And consensus, where we have three terms and this last term is called the consensus term and is unnecessary. It just already agrees with what the other terms indicated is true. And same thing with our dual form. So how do we show that these theorems are true? Well, we can prove they're true through perfect induction or using other theorems and axioms to simplify the equation. In other words, making one side of the equation look like the other. So let's talk about proof by perfect induction. This is also called proof by exhaustion. So we're going to check every possible input value, and if the two expressions produce the same value for every possible input combination, the expressions are equal. And this is pretty easy to do in Boolean algebra because we have a finite number of inputs, right? The input can be either 0 or 1, so we can check it every possible input and prove that it's true for all possible inputs. So here's an example of covering. So we can prove that this is true, B and B or C equals B. Let's prove it's true by perfect induction and then using other theorems and axioms. Here we're going to show that covering is true by perfect induction, so by proof by exhaustion. So here we have the inputs B and C, every possible combination of those inputs. And let's first get this term, B or C. Well, B or C is just 0, 1, 1, 1. And now we're going to AND that B or C with this column, B. B and B or C to get this entire term here. And so we're going to get, well, these top two rows are 0, so 0 and anything is definitely 0. And now these bottom two rows of B are 1, so we get 1 and, well, those are also 1. And so we can see that, well, this column B is exactly equal to B and quantity B or C. And so that's just equal to, right, B and B or C is in fact just equal to B for every possible combination of B and C. And so we've proven by perfect induction or proof by exhaustion that this theorem is in fact true. We can also show that theorems are true using other theorems and axioms. So for example, here we can start with the left side of the covering theorem, B and B or C. And for example, we could use distributivity to say, well, that's equal to B and B or B and C using distributivity. And then we can say, well, B and B is just equal to B using idempotency. And then we get B or B and C. And we could, for example, we could factor out the B and we get B and 1 or C using distributivity in the other direction. And this, we get 1 or C. Well, 1 or C is the null element theorem. Anything in an or relationship with 1 is just going to be 1. And we get B and 1 using our null element theorem. And B and 1 is just identity. Anything ANDed with 1 is just anything. And we end up with equals B using identity. And so we used our other axioms and theorems to show that we started with the left side and we ended up with the right side of that equation. Here's another example of using other axioms and theorems to show that a theorem is true. So let's look at the combining theorem. We have B and C or B and C bar. So we'll start with the left side of this equation, B and C or B and C bar. And we can, for example, use distributivity, what we also call factoring, kind of the reverse direction of distributivity, to factor out, just like in algebra, factor out the B. And so we get B and quantity C or C bar. And now remember that C or C bar is complements, right? One of those is going to be 1, so that's just going to become 1. We'll get B and 1 using complements. And B and 1, that's just identity. Anything ANDed with 1 is just the anything. And so we ended up with the right side of that equation. We started with the left side and ended up with the right side, proving that this theorem, the combining theorem, is true. We have one last theorem called De Morgan's theorem. So it has the theorem and its dual. So the theorem is that the complement of the product is the sum of the complements. So in other words, if we have some product, the complement of that product is equal to the sum, or the OR of the complements. So take each of the term, the OR of the complements. The dual form is the complement of the sum. Right, here's the dual form. We have sum. The complement of that sum, of that OR expression, is equal to the product of the complements. The product, the AND of the complements. And this is called De Morgan's theorem. So here's a recap of all of our theorems of several variables, including the last one we talked about, De Morgan's theorem.